All right, let's continue with the 2-3, 2-4 guided notes. So there's one more thing that I believe is actually in 2-3 that I didn't go over, which just talks about De Morgan's law. So if we're dealing with any two sets, A and B, where both A and B are subsets of the universal set. So that's kind of just implying that you've got some universal set, and A and B are inside that universal set. Not necessarily intersecting, but just drawing that typical picture, then we can conclude that these two things must be true. Both of these are De Morgan's laws. Okay? Now I want to back up a minute and get you to think about something that turned out to be a proof of that. See this right here? Okay? Where when we tried to draw shade what we would have shaded in if we needed the complement of A intersect B, and then tried to shade the set represented by the complement of A, the union of the complement of sets A and B, we wound up getting the same region. Okay, that tells us that those two are equal. So that's this De Morgan's law. That's actually a proof of this one. All right, this one right here is also true, which says if you need the complement of A union B, so I haven't drawn that one yet, I'll do that. Then here's A union B. You want the complement of that. That means you're going to be outside those two sets. And then if I'm trying to figure out, I'm going to do this one in green. So that was me. This is me trying to do the complement of A union B. Now in green, let me try to get the intersection of the complement of A and the complement of B. So here's my A and set B. Okay, so the complement of set A would be here, outside circle A. The complement of set B, I'll do in purple, would be here, outside of set B. Okay, and then if I want the intersection of those two, that would turn out to be, I'll do that in green. The intersection of those two would have to be where I have both blue and purple. And so it would have to be outside of both circles, and that's exactly what I had here. So these are the same. All right, so that's just a proof of it. But if you look at the pattern to try to understand the pattern, notice what it does is if you're trying to do the complement of the intersection, right? The complement of the intersection or the complement of the union of two sets, what you can do is do the complement of each set first, but then notice if it was intersection to start, it's going to become union. Okay, do the complement of each set first, but then if it was union of the two sets, flip it to intersection. And those two sets would have the same meaning. Now here's one place where I could have used that in a problem we've already done. There's one problem where I was asked, okay, right here. Here I was asked to do the intersection of the complement of A and the complement of B. If I knew De Morgan's law, that would be the complement of A union B, right? I could flip this sign, okay, and then look at A union B first and take its complement, which is easier to think about, okay? If I did A union B first, that would be here, right? So the complement would just be outside that, and I'm done. I know it's going to be the set PMZ. It's that quick. Okay? So sometimes knowing about De Morgan's law can enable you a way to work a problem quickly. Okay? All right. Let's go ahead and get into section. Sorry, it's not moving. Okay. Let me go ahead and get into section. It's trying to save. Sometimes it freezes up a bit. Get it moving. Okay, let's get into section 2.4 now. 2.4 is like the water problem, the water activities problem. Okay, when you're given like a survey and you've got these numbers like 93 and 70 represent the number of people that are in a particular region. That's what cardinality is. So these are cardinal numbers, right? Okay, so there's 93 people who like football, 70 like baseball, 40 like hockey. All right, so what I might do is first label these. So I'm going to call this my football circle. I'm going to think about this being my hockey people. Or let me do baseball since it was second. I'll put baseball there. And then these are my hockey people. Okay. Now, I can't put the 93 into the diagram anywhere yet, but I want to remember that 93 people would have to fill in the football circle. So all those regions would have to add up to be 90. Okay, 70 for baseball, 40 for hockey. Okay, really, I don't really get to put those in yet. But if you keep looking, you'll notice they gave us that 20 people like all three sports. So that would be where those three circles intersect. That would be 20. Now, if I know that, that can help me to fill in these regions, because I know this would be the people who like football and baseball are 40, but I already know 20 of them also like hockey, so I would put 20 there. I know 40 should be the total for that intersection between those two circles. Okay. All right, now I know the intersection of these two circles here, football and hockey, is 28, right? So what I'm going to do to get this spot, this particular region, so I'm going to take the 28 and subtract the 20 I already know are in there, which means there's 8 in that region. Okay. And then over here should be baseball and hockey. And by that I mean in this region should be baseball and hockey. And baseball and hockey is 25 people. So 25 people, all total, take away the 20, leaves us a 5. So that idea of subtracting to get what's in each of those regions, that's important. Okay. So now I can fill in this region, because I can take the 93 and subtract the 20 and 20 and 8, the 48. And when I do that, that tells me there should be 45 people right here. And think about it, those people like football and nothing else. Okay. For this region, I know there should be 70 in the whole entire circle, and I've already got 45 in that circle. So I'm going to take that 70. Come on, trying to get it to subtract. Hold on. There we go. So I'm going to take 70 and subtract the 45, and when I do that, I wind up getting 25 people are here. And then for hockey, I know there's 40 all total, and I already have 28, 33 in there. So I know there's 7 that are left there. Okay. All right, now, part of what you had to do was to construct the Venn diagram. Then you were asked to answer the questions that follow. All right, so when they ask me how many people like only football, I need to recognize that the answer to that question would be this region. So my answer would be 45. Okay. Now, if they want to know how many people don't like any of the sports, I have to recognize that 140 people were questioned. So the total of everybody in the Venn diagram anywhere should add up to be 140. Okay? So what I'm going to do for this one is take that 140 and I'm going to subtract all the people in the football circle, which is 93, and then the additional ones I haven't already subtracted would be 25, 5, and 7. So that would be another 37. Okay? Okay, or I could have added the 93 and the 37 up and subtracted it. Okay? So 140 minus 130 means there's 10 people left out here. Those are the 10 people who don't like any of the sports. Okay? Right now, these are the kind of problems where there's like so many different questions you could have been asked. Like, I might have asked for how many people like, so let me just do a what if. How many like football and hockey, but not baseball? Okay, football and hockey, both at the same time. Okay, football and hockey would be here. But they can't like baseball, so you have to not think about those 20, and the answer would be 8. Okay. All right, now here's a question where 50 people were surveyed about their pets, or cats and dogs. So we have information about cats and information about dogs. Many people have both. Okay, so 50 people were surveyed, so there should be 50 in the box altogether. 21 people had cats, means the cat circle all total has to be 21. Okay, 38 had dogs, means 38 people have to be all together in that dog circle. I can't really put those in quite yet. I just know the total for the cat circle and the total for the dog circle. Now, 3 didn't have either a cat or a dog, so I know there's 3 out here. So there's several ways you could think about this problem, but I started by putting in that 3. When I put the 3 in there, then I knew those 3 people don't have cats or dogs, so I subtracted 3 and found out that there should be a total of 47 in both of those circles. All right, so let's think about this. If there's 47 altogether, and I know that here there should be 21, then what I could do is take the 47 and subtract the 21, and that would give me 26, and I know that would have to be this. How many are over there just dogs? Okay, so that's one way to think about it. There's other approaches you might have used, but that is what kind of breaks it open for me. So once I know that's 26, then I can come in here, right? And I can think for a minute, well, if that's 26, then this right here would be 38, take away 26, or 12. So there should be 12 there. And if that's 12, then I know this should be 21, take away 12. Okay, which would give me 9. And then notice the 9 and the 12 would be the total of 21 like I need. The 12 and the 26 gives me the 38 that I need. And if I add up the 9, the 12, the 26, that gives me 47 plus 3, that's the whole 50. Okay, so that's one way to think about it. I've had people do things like 21 plus 38. When you add those up, see how that turns out to be 59. Okay, 21 plus 38 turns out to be 59. Okay, they know that there's supposed to be 47 in those circles. So when they subtract the 47, and they know that because we know 3 are outside, that gives them this 12, so they know the 12 had to have been double counted. So 12 would be in the middle. So just kind of ponder what you would have tried, what you would have thought about there. I tried to approach it in a way that I think most people might think about it, which is 50, 3 that don't have either a cat or a dog, which means 47 left. And then that means the total of everything in a circle anywhere has to be 47. And so that's where I went from there. So I did this first, then I was able to get the middle, and then I was able to get the only cat side. So how many had both cats and dogs, like at the same time, would be 12. And how many had a cat or a dog? And it doesn't, when I use the word or here, I might make this really clear, a cat or a dog or both, okay, because that's what I mean, but sometimes it's not clear. So a cat, a dog, or both, okay. So the or in the usual sense, that would have been the 47. How many had cats and dogs altogether? Would be 12. Okay. What if I asked how many only had cats? What if I did that what if question? Do you see how that would be 9? So there's lots of different questions you might be asked. All right, now there is a formula that we could use to answer questions related to how many elements are in a set. So a while ago I mentioned that when you use that little n, it means number of elements. So like n of a, that means number of elements. N of a, number of elements in set A. How many are in the set, not actually what they are. All right, so here we're being given a problem which wants us to find the number of elements in set A, and we have all this information given to us. So I'm going to do it just without talking about the cardinal number formula, and then I'll show you where the cardinal number formula comes from, and we'll do it that way. So first, without looking at the formula ahead of time, but just thinking about that typical diagram we've been working with, where we have two sets like this. All right, let's see what we can do here. So we know the number of elements in set B is 36. We know the number of elements in A and B, the intersection would be 21, okay? I know the number of elements in A or B should add up to be 78 all total, okay? So you got some different ways you could go about it. But if I know there's 36 in set B and I know there's 21 in the intersection, then wouldn't the number of elements that are just in set B be 36 take away 21? That would give me 15 here. Okay. Now you may not need that information, but sometimes I just fill in my whole as much of my Venn diagram as I can, and then I look at what the question was they asked. Okay. And then I'm thinking that 78 is supposed to be how many things are in all three regions together. But do you notice that this part right here then would be 78 take away 36? And if I did that, I'd get 42. Now you might have thought about that first, that this would have to be 42. Okay? So that all together, you'd wind up with 78 elements in the circles anywhere. All right, so having gone through all of that, here's the problem. When you go to get the number of elements in set A, it is not just 42, is it? The number of elements in A should equal 42 plus the 21, because 21 and 42 are both circle A, and that gives you a total of 63, and that would be the answer. So you can use Venn diagrams to do that, okay? Works well. All right? Now, what I'm going to do right here is I'm going to look at the formula for a minute. So let's just blindly use the formula. It says the number of elements in the union of A and B equals the number of elements in A plus the number of elements in B minus the number of elements in the intersection of the two. So what we could do is plug in what we know. We know that's 78. We know the number of elements in B is 36. Number of elements in the intersection is 21. All right, now, here's the challenge with this. It depends on how much algebra you've had, whether this makes sense to you or not. So if we're looking at this, 36 take away 21 I could do. 36 take away 21, that's going to be 15. So the number of elements in A plus 15 would have to total 78. So to get the number of elements in A, what I could do, boy, I just need a little bit more room. Hold on a second. Let me just get another page right here if I can. Okay. See if I can get some more room down here so I can show you what I want to show you. Let's see if it'll give me another page. Undo. Sorry. Darn it. Just trying to get that problem to show up again. All right. All right, here we are. Okay, sorry about that. So let me show it using that formula. I just tried to get a little more room, but let me make it more clear. So what I could do is, okay, get it back to my drawing. Thank you for your patience. What I could do is do it without the Venn diagram. I could just take this information. That's what I was trying to do here, but let me just start again. So the formula says this. I'll show you why in a minute. It says to get the number of elements in the union, you could take the number of elements in each set and add those up, but you'd have to subtract the number of elements in the intersection, okay? Now, we could just not draw a Venn diagram and use this. 78 is the number in the union. 21, number in the intersection. B had 36, and we're wanting to know the number of elements in A. So this is what we're trying to solve for. This is what we want by itself. So if you know some algebra, what you could do is go ahead and do 36, take away 21. That would be 15. So if I want the number of elements in A to be by itself, I'd have to get rid of those 15, that 15. So I could subtract it from both sides to undo that and make that go away. And I'd wind up with the number of this being 63. So the number of elements in A would equal 63. Okay? So the formula works good if you know the formula. Okay? Venn diagram also works good, but the tricky part on the Venn diagram is recognizing that this is not the number of elements in A. Recognizing that you have to take 42 plus 21 to get the number of elements in set A. Now the reason this formula works when you think about it is if you're looking at two sets and you think about the union of those two sets, okay? Trying to calculate the union of those two sets. If you added the number of elements in A, which would be all of these, to the number of elements in B, which would be all of these, do you notice that you have both the green and the blue shading, okay, there in the middle here? So that means you've double counted that, and that's the intersection of the two. So if you're going to figure out how many elements are in the union of two sets by adding up how many are in A and then adding to that how many you found in B, then you've double counted this in the middle here. This has been double counted. So that's why you have to take away the number of elements in the intersection of the two, because you've counted them twice. That's where that formula came from. That's why it's what it is. Okay? So cardinality is how many elements are in a set. You could use the cardinal number formula for that last problem, or you could reason it out using Venn diagrams instead. And then problems involving survey results like the cat and dog or the water activities problem, those are also in section 2.4.